Welcome to EDU World Space.
So when we're talking about gravitational force and gravitational pull, we first want to think about Newton's law of gravitation. So Newton's law of gravitation, right? So Newton's law of gravitation is that the force of gravity will be equal to the gravitational constant times the mass of object 1 and the mass of object 2, all over the distance between the two objects squared. Specifically, when we're talking about black holes, though, so capital M, we're going to say, okay, well, black holes have something called the Schwarzschild number. So the Schwarzschild number is really the diameter of this black hole, right? So that can be defined as Rs equals 2 times the gravitational constant times the mass of the black hole all over the speed of light squared. This is really important the way I've written it out, just because it kind of shows you that we have two things in common here. We have the gravitational constant and we have the mass of the black hole, right? So let's go ahead and connect the two together using the gravitational constant. So we're going to solve the Schwarzschild number for the gravitational constant. So that leaves us with Rs times c squared equals 2gm. And then we're going to divide out 2m minus 2m. And that gives us Rs times c squared all over 2 capital M equals our gravitational constant, right? So if we were to plug this back in to our law of gravitation, we would end up with something that looks a little like this, right? We would get force of gravitation equals Rs times c squared times the mass of the black hole times the mass of the object all over 2 times the mass of the black hole r squared. So you can quickly see that we can knock out the mass of the black hole, right? So that leads to our final equation of the force of the black hole. So let's say FB, right, will be equal to the Schwarzschild number times the speed of light squared times the mass of the object in question all over 2 times the distance squared. So let's just kind of take a practical look at things. Let's say that we have a 5 kilogram object that is 3,000 miles away, or kilometers. Oh, excuse me, that's kilometers away. So that's going to be 3,000 times 10 to the third meters, right? That's going to be our R. And then our speed of light is a constant. So the speed of light is going to be 3 times 10 to the 8th meters per second. And our gravitational constant will be our 6.67 times 10 to the negative 11th. And that's going to be in newtons, meters squared, kilograms squared. All right, so we have all these players. Let's go ahead and plug them in. Oh, and our RS, sorry, the RS of the black hole in question is super important, right? That's why we're doing this in the first place. So our RS, let me give you a different color. Our RS is going to be 14 millimeters. Once again, we want that in meters. Just make sure that you keep everything, in the same unit as you go along. So 14 millimeters, that's going to be 1,000 millimeters in 1 meter, right? So that's going to end up being 0.014 meters. So if we plug this in, we're going to plug it in up here. So we have 0.014 meters. That's going to multiply with our speed of light squared. So that's going to be 3 times 10 to the 8th meters per second. And we're going to square that. That's also going to be multiplied by the mass of our object in question, so 5 kilograms, all over 2 times the distance between, so that'll be 3,000 kilometers, or 3,000 times 10 to the 3rd meters, right? There we go, all in blue. And that'll end up to be our force of the black hole. So if you do want to resolve the numerator and the denominator, this will simplify to 6.3 times 10 to the 15th over 1.8 times 10 to the 13th. And of course, we're going to resolve that even further, and that will give you 3.5 times 10 to the 2nd, or 350. And if you want to do the math as far as the, excuse me, this is squared. All right, if you want to do the math and the units, we have meter squared down here, meter squared here. These will cancel out as well, because of the kilograms. You'll get 1 meter down there, you'll get a kilogram, and it'll be divided by seconds squared. So what that leaves us with is a Newton, right? So we have 350 newtons, just kind of the gut check, that all makes sense because Newton is our unit for force. However, if we want to know something different about this black hole, so say that we actually just wanted to know the mass of the black hole. Well, if we do it this way, we actually kind of skip over that part, right? Because it cancels out. So if we wanted to know the mass, we have to go back to our Schwarzschild number, right? So once again, our RS equals 2 times the gravitational constant times the mass of the black hole in question over the speed of light squared. So that means that we have to rearrange this again, right? 2gm over c squared. So if we're rearranging this again, so let's go ahead and do that in pink. This is now going to be RS times c squared all over 2g. This is going to leave us once again with the mass of our black hole. So we have all of these players, right? So if we were to do the math for all of these players, it would look a little bit like this, 0.014 meters times our speed of light squared. So it's 3 times 10 to the 8th squared, all over 2 times our 6.67 times 10 to the negative 11th. And if you once again resolve this, you're going to end up getting something around 9.44 times 10 to the 24th. So that would be in kilograms. Once again, we're talking about mass. If we wanted to do this again, it's meters times meters per second. That's going to end up being squared all over our constant. So that's going to be newtons per meter squared, kilograms squared, right? And that would resolve down into just 1 kilogram, because remember, our newtons are mass times acceleration. So that's going to be a kilogram per meter second squared. That is a Newton. So we end up getting kilograms here. So that kind of sums up how you can get from Newton's law of gravitation, use the Schwarzschild number to understand the relationship between a black hole and the law of gravitation, and some practicalities in plugging in numbers.